3 years ago, Unity released a mega city demo, a complex real-time game scene with millions of objects, light sources, and audio sources, all being rendered in real time. It had over 100,000 audio sources, one for each car, neon sign, and more, creating a rich and complex soundscape. But how did Unity manage to achieve such high levels of performance and handle millions of objects? And as a backend developer, can we accomplish the same? Hi, I'm Pankaj Basnal and this is Coding Quest, a YouTube series where I experiment with different programming ideas and prototypes. And this time, we are going to explore a high-performance coding architecture called Entity Component System. Before we dive into what ECS is, we need to understand the problems and shortcomings of writing code in object-oriented paradigm, the most famous coding style on which most of modern-day softwares are built. In object-oriented approach, we model our problem in terms of objects which can encapsulate data and behaviors. Let's take a common example from Animal Kingdom. Suppose we have a bird, and a bird can get hungry and tired. So we will have some data to keep track of its hunger and its tiredness. But is it really a bird if it cannot fly? So we will have another data to keep track of how fast it can fly. Next we will add behaviors or functions to act on this data, eat, sleep and fly to perform their respective behaviors. Similarly, we can add a fish, but instead of flying, it can swim. And here we get into our first problem, duplicate data and duplicate behaviors. And code duplicacy is a really bad thing in software engineering. We can solve this problem by using a concept called inheritance. We basically create a hierarchy of parent and child classes, and we move all the common data and behaviors to the parent class, while the child class can directly use it. Phew! Crisis averted. But what about a flying fish? A creature that can fly and swim and row in the hierarchy. We can inherit it from both bird and fish, but that would lead to the diamond inheritance problem, which makes the code very messy, and most of the object-oriented languages don't support it. We can inherit it directly from the animal class, but that would again lead to duplicate code. There are ways to solve this problem, but I want to bring the focus to the rigidity of this approach. Once the hierarchy has been established, it is very difficult to change it, and any new requirement that challenges this hierarchy can break the code. This is where entity component system is most valuable. In ECS, we split the data from the logic. The raw data is called components, and the logic and behavior is called system. So, an entity is just a collection of components. Let's take a look at our problem from the ECS point of view. So we will have three entities, flying fish, fish and bird, and our systems, eat, sleep, fly and swim. And we give the desired behavior to our entities by adding the corresponding component. To see how flexible this is, let's say we need to create a zombie fish, which can get hungry and it can swim, but it cannot get tired and it cannot fly. On top of that, it would need a new system called zombie. Now, if we want to create a zombie bird, all we have to do is add the zombie component to it. This is like building with Lego pieces, without any rigid hierarchy. Extending our program this way is as simple as adding relevant components in system and composing them together to create the desired object. Now I know that this sounds like a dream come true, and things always look good on paper, but the reality could be really complicated. So ECS doesn't promise us that it will solve all our problems, but it gives us an architecture which is very flexible to change, evolve and adapt to our ever-changing requirements. With that said, we should now look at an implementation to better understand it. An entity truly contains just an ID and a collection of components. A component will only contain the data that is relevant to it, and systems contain logic to get the relevant component and execute the required behavior. To tie all this together, we create the entity, we add the relevant components, and we execute all the systems on it. This simple implementation of ECS is not going to give us any performance benefits, but it is still an incredibly useful tool to create a highly flexible software. In the next part of the video, we will look at how ECS can help us create a high-performance code architecture. But before we get there, we need to understand a few complicated concepts, so buckle up. Whenever we try to access any data in our code, The CPU first goes to CPU cache, and if it's a miss, it checks with the RAM. If it finds the data there, it will put that data inside cache so that it doesn't miss it the next time it is trying to access it. This is where CPUs use a little trick, and they pull in extra data in hope that if our code needs it, it doesn't have to go to the RAM again. CPUs use this trick because a RAM can be anywhere between 10 to 100 times slower than the cache. Armed with this knowledge, it's time to look at the code from a new perspective. For demonstration purpose, I'll be using swimming info of the fish to update its position. In this, we will observe what happens when we call swim on two different instances of fish. Their position data will be instantiated in memory at two different locations. This is because classes are reference types and they are stored in memory at a random location. Running this code for fish 1, when we try to access its position data, the request goes to the CPU and CPU will check in the CPU cache. It will be a miss and then CPU will have to get the data from RAM. The same thing will happen when we call the swim function on fish 2. Our code will ask for the position data and CPU will try to get that from the CPU cache, but it will be another cache miss. So CPU goes to RAM and fetches the position data from RAM. So for every fish, we are encountering a cache miss. So if we have 10,000 fishes, we will encounter 10,000 cache misses. We understand the problem now. How does ECS solve it? The answer is quite simple actually. If you look at the problem, it is happening because we are trying to store reference types in memory and CPU is not able to optimize CPU caching for them. So instead of using reference types, we use value types, and instead of storing them randomly in memory, we store them in contiguous memory allocation using arrays. We will have to make a few tweaks to our current implementation of ECS. First of all, we will remove the components map from our entities and then store the components inside arrays. Sounds real. Let's take a look at the code. As you can see, entity now only contains a field ID. And another change that you would notice is both entity and components are now structs. Structs are value type and they give us a better control over their memory layout. Another change you will notice is the use of scene object. Since entities don't contain their components anymore, scene object does the mapping between entity and its components. Here's the implementation of scene. It uses the object pooling pattern to map the component type to the array of its components. So if the entity has ID 2, its position component will be stored at the second index of position component array. Time to see how all this comes together to optimize for CPU caching. We will again take the example of two swimming fishes and their position component, which this time will be stored adjacent to each other in memory. This is because position component is a value type now and stored in an array. Running the loop for fish 1, we will try to access its position component. Request goes to CPU, CPU tries to get it from cache. It will be a cache miss. So CPU goes to RAM and fetches the position component of the first fish. But because of its optimization, it also gets the position of second fish. Now when the loop runs for the second fish and our code asks for position of second fish, the request goes to CPU and this time CPU finds the data in cache and there won't be a cache miss. So in this scenario, we were able to use CPU's caching mechanism to optimize our code and make it run 2 times faster. But keep in mind that there are many things happening under the hood and the real numbers might differ. Concepts like boxing and unboxing of objects can impact the performance. On the other hand, CPUs have multiple tricks like prefetching, which can also improve the performance. So I recommend trying it out for yourself to get a better understanding of what is happening. Like in the code that I have shown in this video, I ran it for 10 million objects and I was able to get 5 times performance benefit.